In the year 1878, inside a massive industrial forge in Le Creuset, France, workers gathered beneath a machine that looked less like a tool and more like a towering iron monument. The structure rose several stories above the factory floor, its dark metal frame stretching upward like the skeleton of a giant building. Suspended at the center of that frame hung the heart of the machine, a colossal hammerhead weighing several tons. To the men working below, it felt as if they were standing beneath a sleeping giant. Steam drifted through the air, mixing with the heat of glowing furnaces and the smell of burning coal. Chains creaked overhead as cranes slowly moved enormous pieces of red-hot metal across the forge. Sparks occasionally burst from the furnaces, floating through the smoky air like tiny fireflies. Then the signal came. High above the floor, the hammer operator opened the steam valve. With a deep mechanical groan, the massive hammer began to rise. The piston lifted it slowly upward along the tall iron frame. Workers below stepped back carefully, their eyes fixed on the glowing ingot sitting on the anvil. For a brief moment, the machine seemed to pause. The hammer hovered high above the metal, suspended in the smoky air like a storm waiting to break. Then the operator released the valve. The hammer dropped. When it struck the anvil, the sound exploded through the factory like thunder trapped inside iron walls. The impact was so violent that sparks burst outward in every direction. Chains rattled, tools jumped across work tables, and the ground beneath the workers' boots trembled with the force of the blow. Some men later joked that every strike made their teeth rattle. Others said the vibration traveled straight through their bones. But the noise wasn't the most frightening part. The real danger was the distance. Dozens of workers had to stand only a few feet away from this giant machine while it operated. Their job was to guide massive pieces of glowing iron into position beneath the hammer. Using long tongs and hooks, they moved quickly across the factory floor, carefully positioning the metal before each strike. Every movement had to be perfectly timed. If a worker hesitated, if the metal shifted unexpectedly, or if a tool slipped at the wrong moment, the hammer would not stop. Once the operator released the valve, gravity and steam pressure took control. The hammer would fall exactly as designed, delivering a crushing blow powerful enough to reshape glowing iron like soft clay. For the men working beneath it, every strike carried a silent question. Would the hammer shape the metal, or would something go wrong? And yet, despite the danger, these machines quickly became essential to the rapidly growing industrial world. Factories depended on their incredible power to produce the massive metal parts needed for ships, engines, and railways. But before machines like this existed, forging metal looked very different. In fact, the entire Industrial Revolution nearly stalled because the world simply didn't have a machine powerful enough to shape the iron it needed. Until one engineer decided to build a hammer unlike anything the world had ever seen. Long before the thunder of steam hammers echoed through giant factories, forging metal was a far slower and far more exhausting process. In the early 1800s, most metal shaping still relied on the same basic method that blacksmiths had used for centuries. Inside small, smoke-filled forges, glowing pieces of iron were pulled from blazing furnaces and placed onto heavy anvils. Around the anvil stood a team of workers, each gripping a long-handle hammer. Their faces were blackened with soot, their clothes soaked with sweat from the furnace heat. When the foreman shouted a command, the workers raised their hammers together. Then they struck. Heavy iron hammers crashed down again and again in a carefully timed rhythm. Sparks exploded outward with every blow, while the metal slowly began to change shape. It was exhausting work that demanded strength, precision, and perfect coordination. If the workers missed their rhythm, the metal could bend unevenly. If the iron cooled too quickly, it would become too hard to shape at all. That meant the entire piece had to be reheated, wasting time and fuel. For centuries, this method had worked well enough. Blacksmiths forged tools, weapons, horseshoes, and small machine parts using teamwork and muscle power. But by the early 19th century, something extraordinary was happening across Europe and America. The Industrial Revolution was transforming the world. Factories were growing larger every year. Steam engines were becoming more powerful. Railways were spreading across countries, and engineers were designing ships and machines on a scale humanity had never attempted before. Suddenly, industry required enormous pieces of metal. Steamships needed gigantic engine shafts. Railways required huge iron components for locomotives and bridges. Factories demanded heavy gears and massive machine parts capable of withstanding incredible mechanical forces. The problem was simple. The metal parts engineers wanted to build were becoming far larger than the tools used to forge them. Even the strongest teams of hammermen could only deliver so much force. 20 men swinging heavy hammers could shape moderate pieces of iron, but when the metal became extremely large, human strength reached its limit. And worse, human hammering was never perfectly consistent. Some blows landed harder than others. Some strikes missed slightly. Even small differences could weaken large metal parts. As industrial machines grew bigger, these inconsistencies became dangerous. Engineers needed metal components that were not only large but also strong and precisely shaped. A weak shaft in a steam engine or ship could break under stress and cause catastrophic failure. It became clear that traditional forging methods were reaching their limit. Industry needed something new, something far more powerful than a team of hammermen. Some engineers began imagining a machine that could deliver massive hammer blows again and again with perfect control. A machine powered not by human muscle, but by the incredible force of steam. At first, the idea sounded almost impossible. But soon, one engineering challenge would push the limits of metal forging so far that inventing such a machine became the only solution. In 1839, one of the most ambitious engineering projects in the world was taking shape along the banks of the River Avon in England. The project was bold, expensive, and unlike anything the shipbuilding industry had attempted before. It was called the SS Great Britain. Designed by the brilliant engineer Isambard Kingdom Brunel, the ship was meant to revolutionize ocean travel. Unlike most ships of the time, which were made of wood and powered by sails, Brunel's vessel would be built almost entirely from iron and driven by powerful steam engines. It was a bold vision of the future, but that future created a problem no forge in Britain could solve. To power the ship's massive paddle wheels, Brunel required a gigantic iron paddle shaft nearly 30 inches thick. This single metal component had to be forged from one solid piece of iron, strong enough to endure the enormous stresses of ocean travel. At first glance, it might not sound extraordinary, but in the 1830s, forging a metal shaft of that size was nearly impossible. Traditional blacksmith teams simply didn't have the strength to shape such a massive piece of metal before it cooled. Even if dozens of hammermen worked together, the blows would be uneven and inconsistent. The metal could warp, weaken, or crack during the forging process. If that happened, the entire part would fail. And if the shaft failed, the ship's engines would fail with it. Brunel's project suddenly faced a serious obstacle. The engineers building the ship had the designs. They had the materials. They had the vision for a new age of steam-powered travel. But they lacked the tool powerful enough to forge the metal they needed. That challenge eventually reached the ears of a Scottish engineer named James Naismith. Naismith was already known for designing innovative machine tools. When he heard about the forging problem, he began thinking about a completely different way to strike metal. Instead of relying on teams of workers swinging hammers, Naismith imagined a machine that could deliver enormous hammer blows using steam power. His idea was remarkably simple. A large steam cylinder would lift a heavy hammer block high above an anvil. When the steam pressure was released, gravity would pull the hammer straight down onto the metal below. Unlike swinging hand hammers, the blow would travel in a perfectly vertical line. Even more important, the force of each strike could be carefully controlled by adjusting the steam pressure. The machine could deliver powerful blows again and again without fatigue, without uneven strikes, and without the limits of human strength. If Naismith's design worked, a single machine could perform the work of dozens of hammermen. More importantly, it could shape the enormous metal parts the growing industrial world demanded. What began as a simple sketch on paper would soon become one of the most powerful machines of the 19th century. But first, someone had to build it. When engineers first looked at James Naismith's steam hammer design, the concept seemed surprisingly simple. On paper, it looked almost like an upside-down steam engine. A tall iron frame would support a vertical steam cylinder, and attached to the piston would be a massive hammer block that could rise and fall along guide rails. The idea was elegant. Steam would lift the hammer upward, and gravity would bring it crashing down. But turning that simple idea into a real machine required solving a much larger problem: scale. The moment factories realized how powerful this new invention could be, they began thinking bigger. If a steam hammer could replace dozens of workers swinging hand tools, then building a larger hammer meant delivering even more force. Within a few decades, steam hammers began growing into enormous industrial machines. Some stood 3 or 4 stories tall, their iron frames rising high above the forge floor like skeletal towers. Thick steel guide rails kept the hammer aligned as it moved up and down, while giant pistons inside steam cylinders lifted the hammer head with incredible power. At the center of the machine was the hammer itself, a massive iron block weighing several tons. Suspended high within the frame, it could be raised slowly with steam pressure before dropping onto the glowing metal plate on the anvil below. But lifting a hammer this large was only part of the challenge. The real problem came when it struck. Every time the hammer fell, the impact generated enormous shock waves that traveled through the machine and into the ground beneath it. Without a strong foundation, those violent vibrations could tear the entire structure apart. Engineers quickly realized the machine needed a base as strong as the hammer itself. At major forging works like Le Creuset in France, builders constructed gigantic foundations beneath the forge floor. Heavy stone blocks, timber layers, and deep masonry supports were stacked far below the surface to absorb the shock of each strike. In some cases, the hammer's foundation extended several meters into ground, anchoring the machine firmly to the earth. Above this massive base stood the towering iron frame. Visitors who saw these machines for the first time were stunned by their size. The hammer frame stretched high into the smoky air of the forge, their tall iron legs forming an open triangular structure that reminded many observers of a giant metal tower. Some even compared their outlines to the shape of the Eiffel Tower. But unlike a monument meant to be admired from a distance, this iron giant was built for brutal work. Every few seconds, the hammer would rise slowly along its guide rails. Workers below would rush to position glowing metal beneath it. Then the operator would release the steam, and the hammer would fall. With each thunderous strike, the machine delivered a blow powerful enough to reshape massive pieces of iron. But beneath that towering frame, men had to move quickly and precisely, because once the hammer started falling, nothing could stop it. To an outsider, the giant steam hammer looked like a magnificent machine, a triumph of engineering and power. But to the men who worked beneath it every day, the hammer was something else entirely. It was a discipline of timing. Inside the forge, the environment was overwhelming. The air was thick with heat from massive furnaces where iron glowed bright orange. Smoke drifted toward the ceiling, while sparks burst from the metal like tiny fireworks. The constant noise of machinery, cranes, and clanging tools filled the building, and above it all stood the hammer. The massive iron frame towered high above the factory floor, while the hammer head moved slowly along its guide rails. Suspended inside the frame, It looked almost calm while it waited for the next strike. But the workers knew better. Because every time the hammer moved, dozens of men had to move with it. A typical forging operation began when a glowing metal ingot was removed from the furnace. These ingots were enormous, sometimes weighing many tons, and they radiated heat intense enough to burn exposed skin within seconds. Using long steel tongs and heavy hooks, workers guided the blazing metal across the forge floor toward a hammer's anvil. Overhead cranes assisted by lifting the heavier pieces, but the final positioning often depended on human hands. Every worker had a role. One crew guided the metal into place. Another controlled the cranes. Others watched the hammer operator above, waiting for signals that told them when the hammer would rise and when it would fall. Then everything happened quickly. The hammer began to lift. Steam hissed through the pipes as the giant piston slowly raised the hammer head into the air. Workers rushed forward to adjust the position of the glowing metal on the anvil. Using long-handled tools, they rotated the piece, aligned it, or held it steady for the next blow. The operator watched carefully from his platform high above the floor. He read the signals from the crew below. Hand gestures, tool movements, quick glances. When everything looked ready, he released the steam pressure, and the hammer dropped. The impact was thunderous. Sparks erupted outward, and the glowing metal flattened slightly under the force of the blow. Workers immediately rushed forward again, adjusting the metal for the next strike, before the hammer rose once more. The entire process looked almost like a carefully choreographed dance. But the dance had no room for mistakes. If the metal shifted unexpectedly, it could twist or jump when struck. If a worker moved too slowly, the hammer might fall before the tools cleared the anvil. Even a small misalignment could send fragments of hot metal flying across the floor. Despite the danger, experienced crews developed incredible skill. Some steam hammers became famous for their precision. Stories circulated through the industry, claiming that a skilled operator could control the hammer so gently that it could tap the cork into a bottle without breaking the glass. Moments later, the same machine could deliver a crushing blow strong enough to reshape a massive steel ingot. That balance between control and destruction fascinated engineers and terrified workers, because everyone in the forge understood one simple truth. The steam hammer was only as safe as the people controlling it. A skilled crew could operate the machine with astonishing precision, shaping metal exactly as needed. But if fatigue slowed someone's reaction, if communication failed, or if a worker made a single mistake, the machine would not hesitate. The hammer would still fall. And when several tons of iron dropped from above, there was no time to escape. That was why veteran forge workers treated the steam hammer with a kind of quiet respect. To them, it was more than just a machine. It was a sleeping giant, calm when handled with skill, but always capable of unleashing tremendous force if something went wrong. And every shift inside the forge meant standing beneath that giant once again, trusting that timing, teamwork, and experience would keep the next blow exactly where it belonged. At first glance, the giant steam hammer seemed like the most dangerous thing inside the forge. After all, it was a towering machine capable of delivering crushing blows powerful enough to reshape massive blocks of iron. But the experienced workers knew something outsiders rarely understood. The hammer was only one danger among many. The real risks were hidden in the chaotic environment that surrounded it. Inside a large 19th century forge, the floor was constantly in motion. Furnaces roared with intense heat, while molten metal glowed bright orange inside heavy containers. Overhead cranes creaked along iron rails mounted near the ceiling, carrying enormous loads of red-hot metal from the furnace toward the hammer. Each of those glowing loads could weigh several tons. They moved slowly through the air, suspended by thick iron chains and massive hooks that strained under the incredible weight. And every worker on the forge floor knew the same terrifying fact. If one of those chains failed, the falling metal would not bounce. It would crush whatever was beneath it. The cranes were essential for moving heavy ingots, but they also created constant tension in the workshop. Workers watched the loads carefully as they swung overhead, knowing that heat, dust, and vibrations slowly weakened the metal links, holding everything together. Sometimes a chain looked perfectly strong until the moment it snapped. When that happened, the glowing iron could fall without warning. Even the forge floor itself was dangerous. The ground was often covered with fragments of metal, slag from previous forging operations, and small pieces of broken tools. These debris scattered across the surface made footing uncertain, especially for workers carrying heavy equipment or guiding hot metal. But the most difficult task in the forge was the run from the furnace to the hammer. When an ingot came out of the furnace, it had to be shaped quickly before the metal cooled and hardened. That meant workers had to move the glowing mass to the hammer as fast as possible. There was no time to rest. The metal could not simply be set down while workers caught their breath. Every delay meant the iron losing heat and becoming harder to forge. So the crews pushed forward quickly, guiding the massive glowing pieces across the floor, while cranes lifted the heavier loads overhead. The danger came when something unexpected happened. If a cart struck a piece of debris, if a worker slipped on the floor, or if the metal shifted inside its container, the entire load could tip. Historical records from several factories describe horrific accidents that occurred during these moments. In one case, a worker pulling a glowing mass toward the hammer slipped on the forge floor. The heavy container tipped forward, spilling the red-hot metal onto him before the crew could react. Despite their efforts to pull the load away, the injuries proved fatal. And even when nothing fell, another invisible danger remained present throughout the forge. Steam. The giant hammer depended on pressurized steam moving through pipes, valves, and cylinders. That steam carried enormous energy. If a pipe cracked or a valve failed, the pressurized vapor could escape instantly. Unlike fire, steam could burn skin in seconds while remaining nearly invisible. Workers sometimes did not even realize a leak had occurred until it was too late. Then there was the constant strain placed on the workers themselves. The forge was loud enough to drown out shouted warnings. The heat from furnaces could be exhausting after hours of work, and the intense concentration required to guide heavy metal beneath the hammer left little room for mistakes. Fatigue slowly built throughout each shift. Hands became slower. Reactions became delayed. Judgment became less precise. Under normal circumstances, small human errors might go unnoticed. But inside a forge filled with enormous machines and glowing metal, those tiny mistakes could escalate quickly. That was why veteran workers believed the greatest danger in the forge wasn't the hammer alone. It was a combination of heat, pressure, heavy machinery, and human exhaustion, all operating together in a place where a single moment of misjudgment could trigger a disaster. And every worker who stepped onto that forge floor understood one thing. Surviving the day required far more than strength. It required constant awareness and a deep respect for the machines surrounding them. By the late 1800s, the thunder of steam hammers had become a familiar sound across the industrial world. Inside massive forging works in Europe and America, these tower machines struck iron day and night, shaping the metal backbone of a rapidly changing civilization. What began as a solution to a single engineering challenge had quickly become one of the most important tools of the Industrial Revolution. Factories depended on the steam hammer's incredible strength. The machine could forge enormous metal components that no team of workers could ever shape by hand. Giant engine shafts for steamships, massive locomotive parts for railways, heavy artillery components, bridge supports, and industrial machinery were all produced beneath these powerful machines. Every strike helped build the infrastructure of a new industrial age. Railroads stretching across continents required powerful locomotives and strong metal parts. Steamships crossing the oceans needed durable engine shafts capable of withstanding enormous mechanical stress. Even factories themselves relied on heavy gears and machine frames forged by steam hammers. In many ways, the steam hammer became the heartbeat of industrial production. The rhythm of its strikes echoed through entire factory districts. Workers living in nearby towns could often hear the hammer blows carrying through the air, a deep metallic thunder that repeated throughout the day. For the engineers and factory owners, the steam hammer symbolized progress. It allowed industry to grow faster than ever before. Machines could be built larger, stronger, and more powerful because factories finally had a tool capable of forging metal on that scale. But progress always brought new competition. As industries expanded, engineers constantly searched for ways to improve efficiency and reduce risk inside the forge. The steam hammer delivered incredible force, but its violent impacts also placed tremendous stress on machines, tools, and foundations. Each blow sent shockwaves through the forge structure. Over time, those impacts could damage equipment and even weaken the surrounding building. Engineers began experimenting with new forging technologies that used pressure rather than repeated hammer strikes. One of the most promising alternatives was the hydraulic press. Instead of dropping a heavy hammer block onto metal, hydraulic presses applied enormous force slowly and evenly. The metal could be shaped under steady pressure rather than violent impacts, allowing greater control over the forging process. These presses also reduced some of the dangers that came from flying metal fragments and sudden hammer blows. By the early 20th century, many factories began installing hydraulic presses alongside their steam hammers. In some cases, the new machines gradually replaced the giant hammers entirely. The change was not immediate. Steam hammers had proven their reliability over decades of industrial use. Many forging works continued using them for years because the machines were already built, and experienced crews knew how to operate them safely. But the industrial world was evolving once again. New technology promised more control, greater efficiency, and safer working conditions. Slowly, the thunderous rhythm that once dominated factory floors began to fade. Some of the largest steam hammers were dismantled as factories modernized their equipment. Others were retired after decades of service, their towering frames left standing as reminders of an earlier industrial era. Yet even as newer machines replaced them, the legacy of the steam hammer remained unmistakable. For nearly a century, these iron giants had shaped the metal parts that powered ships, trains, factories, and machines around the world. Without them, the Industrial Revolution might have advanced far more slowly. The steam hammer had done exactly what it was built to do. It had given industry the power to shape the future, one thunderous strike at a time. Today, if you walk through certain industrial museums or old town squares in Europe, you might still find one of the great steam hammers standing silently in the open air. Their massive iron frames tower above visitors, the giant hammerheads frozen in place as if they are waiting for one final strike. But the factories around them are quiet now. The roaring furnaces are gone. The cranes no longer creak overhead. And the thunderous blows that once shook entire buildings have faded into history. Yet these enormous machines still carry a powerful presence. Standing beneath one of these preserved steam hammers, it is easy to imagine the world that once surrounded them. The smoky air of the forge, the glowing iron resting on the anvil, the nervous glances exchanged between workers as the hammer slowly rose above their heads. For decades, these machines stood at the center of industrial progress. They forged massive engine shafts that powered steamships across the oceans. They shaped locomotive parts that pulled trains across continents. They produced metal structures that helped build bridges, factories, and machinery across the industrial world. In many ways, the steam hammer became a symbol of the age itself, an era when technology began transforming the scale of human ambition. But the story of the steam hammer is not only about engineering achievement, it is also about the people who work beside these machines. Every day, workers stepped onto forge floors knowing they would spend hours guiding glowing metal beneath machines powerful enough to crush steel. Their skill, timing, and teamwork were the only things separating controlled production from disaster. The hammer obeyed its design, but it was human judgment that made it safe. Veteran forge workers understood this better than anyone. They respected the machine's power, not because it was unpredictable, but because it was perfectly predictable. Once the hammer started falling, nothing could stop it. That simple fact shaped the discipline of the forge. Workers learned to trust one another's timing. Signals were passed quickly between crews. Experienced operators developed an almost instinctive sense of when to slow the machine or hold the hammer above the anvil. In a strange way, the steam hammer became more than just a machine. It became a test of human skill. And for many workers, surviving years beneath those tower machines became a source of quiet pride. The soot-covered faces, the tired bodies at the end of long shifts, and the scars carried by some workers all told the story of a demanding industrial life. Eventually, technology moved forward once again. Hydraulic presses and modern forging systems replaced many of the giant steam hammers. These newer machines could shape metal with smoother pressure and often improved safety. The iron giants that once dominated factory floors slowly disappeared. Some were dismantled, others were preserved as historic landmarks. But the legacy they left behind remains enormous. The steam hammer helped make large-scale industrial manufacturing possible. It allowed engineers to build bigger machines, stronger ships, and more powerful engines than the world had ever seen before. In many ways, these tower machines helped shape the modern industrial world. And perhaps that is why the old steam hammers still capture our imagination today. They remind us of a time when the future of industry depended on machines powerful enough to shake the ground, and on the men brave enough to stand beneath them